students. Today we'll discuss about optical instruments. What are these optical instruments? These are the devices which have been designed using the refracting properties of mirror and lenses and prisms. So using the optical properties, whichever devices have been designed, those are called as optical instruments. Among those, first we'll see about microscope. What is microscope? The name itself indicates. Micro means small. Microscope means the device which enables us to see the small things. Now, how it enables? It doesn't mean that the microscope itself is increasing the size of the object to enable us to see that. It is enlarging, or it is producing an enlarged image of that object, so that we can view the image of that object, a clear image. So how it is possible to form a enlarged image? By placing the object at a suitable distance. Now in that, the first one is in a microscope. The first one is simple microscope, a basic model. So simple microscope is a converging lens of a small focal length. Converging lens means a convex lens. A convex lens which is having a rim support over it. So it is nothing but a convex lens. How to use this lens? The lens is held near the object, and eye is positioned on the close to the lens on the other side. Why the object has to be held near the lens? To get an erect, magnified and virtual image, because you know the image formation pattern for a convex lens. If the object distance is greater than f, if the object distance is greater than f, the image formed will be real and inverted. If you want to have erect image, the object distance should be less than focal length. So the object is held near the converging lens or near the simple microscope or a magnifying lens. Now, where the image has to be formed? The image has to be formed in such a way that the eye can see it clearly. So here we discuss two extreme cases. It is, one is at minimum, another one is at maximum. So image formed at a minimum distance from the eye, image formed at maximum distance from the eye. Now what is this minimum distance? It is nothing but least distance of distinct vision, which is denoted by capital D, least distance of distinct vision, capital D. What does it mean? So capital D is the minimum distance from the eye for which the eye can see the clear image. So for a normal person, normal adult, it is about 25 centimeter. It means if you hold an object or an image, whatever it is, less than 25 centimeter, the eye cannot see it. It cannot see it clearly. A blurred image is formed on the retina. So whatever the eye want to see, it should be at least at a distance of 25 centimeter or more than that. So 25 centimeter or D is the minimum distance the eye can see the object or the image. So the image formed by the converging lens or by the simple microscope should be at least at 25 centimeter, not less than that. So this is the minimum distance of image formation by the simple microscope, so that the eye can see it. The other possibility is, the other extreme condition is at a maximum distance. Maximum is nothing but infinity. So forming the image at 25 centimeter causes strain on eye. Therefore, the image formed at infinity is often considered most suitable because the eye will be in a relaxed position to observe that image which is formed at infinity. So here we are going to see the two extreme cases: image formed by the simple microscope at minimum distance, that is at capital D, least distance of distinct vision, and image formed by the simple microscope at infinity. So in both the cases we are going to see what is the nature of the image formed or what is the magnification caused by the lens. So the first case is equation for linear magnification when the image is formed at capital D. So a converging lens, in front of that lens we are placing an object at a distance of u, and that u is less than f, that u is less than f, so that we can get a erect and virtual image. If it is more than f, we are going to get a real image on the other side of the lens, and it will be inverted. We want to have the object, the image on the same side of the object, that is a virtual image. So we have to place the object at a distance less than focal length. So object is placed at a distance of u and image has to be formed at a distance of d from the eye. From the lens means already we have discussed the eye is positioned near close to the lens on the other side. So here is the eye positioned near the lens. So the image is formed at a distance of d. Now from the equation, thin lens formula, it is 1 upon f is equal to minus 1 by u plus 1 by v. Multiply this equation throughout by v. You are going to get v by f is equal to minus v by u plus 1. V by v is plus 1. If you rearrange the equation, it will be minus v by u. You take it on the other side. V by u. V by f on the other side will be minus v by f plus 1. So 1 minus v by f. And from the definition of magnification, m is v by u. Magnification is always image by object. That is either image distance by object distance, image height by object height, or the next session you are going to see it is theta dash by theta, that is angle subtended by the image divided by angle subtended by the object. So in case of lens, it is v by u is equal to m, linear magnification. So v by u we are replacing by m, 1 minus. Now f is focal length. What about the v? Image distance. It is where the image is formed at a distance of capital D. So v is equal to d. What about the sign convention? This is the direction of the incident ray and our measurement is opposite to the direction of the incident ray. So d is minus. So substitute v is equal to minus d. We are going to get plus d. 1 plus d by f is the magnification formula for the simple microscope when the image is formed at a distance of capital D. Now for a normal adult, capital D value is 25 centimeter. So we can have a magnification of, to have a magnification of 6, one needs a convex lens of a focal length 5 centimeter. If you manufacture a convex lens of focal length 5 centimeter, the m value will be 6. That is, the image formed by the convex lens or image formed by the simple microscope is 6 times larger than that of the object. Now, tell me what is the work of this simple microscope? It is enabling us to see the object. How? By forming its enlarged image, a magnified image. So how much it magnifies? Depending on that, we can see the clear image or clear picture of that object. So here, this is the magnification formula for a simple microscope. The second case is, in the simple microscope only, a second case is the image should be formed at a distance of infinity, at a distance of infinity. So when it is possible to have the image at infinity, the object has to be placed at focal length. So object has to be placed at principal focus f or at a distance of focal length, so that image formed will be at infinity. So at infinity the image formed will be inverted, but we want an erect image. For erect image, what should be the object distance? Less than focal length. So what will do? The object is, see, the object is at a distance of f, the image is at infinity. So at infinity, image nature will be inverted, but we want erect image. So what will do? The object is slightly less than focal length. To have a erect image, object is placed slightly less than focal length, almost near to focal length only, so that you can take u is equal to f. You can take, so u is equal to nearly equal to f only, but it is placed slightly less than focal length to have an erect and virtual image. If the object distance is slightly less than focal length, the image formed is nearer to infinity, not exactly at infinity, nearer to infinity, so that approximately you can take it as infinity only, nearly infinity. And what is the nature? An erect image. Now here, to have the magnification formed by the simple microscope, we are considering the angular magnification. Angular magnification means magnification is equal to, as you have v by u, we can have theta dash by theta. It is angle formed by the image at I divided by angle formed by the object at I. So maximum angle formed by the object at I. So if you place an object at a distance of d, because you cannot place the object place the object less than d, because I cannot see that. So the minimum distance where you can place the object in front of I is d. So h is the height of the object, and theta naught is the angle subtended by the object at I. So theta naught, angle subtended by the object at I. Here we are considering without the lens. Without the lens, so this angle is maximum when the object distance is d. So theta naught is nearly equal to tan theta naught. For small angle approximation, you can get tan theta is nearly equal to theta. So theta naught is nearly equal to tan theta naught. What is the value? Opposite upon base, h by d. So h by d is nothing but theta naught, which is the angle subtended by the object at I. Now from the relation, h dash by h, image height by object height, is nothing but magnification. It is also equal to v by u. So you can write h dash by h is equal to v by u. When you rearrange the equation, h dash is equal to hv divided by u. Now wherever h dash value you get, you can substitute hv divided by u. Now we'll write the equation for angle subtended by image at I, theta I. So here is the image which is forming an angle theta I at I. Height of the image is h dash. The distance of the image is v. So for small angle approximation, tan theta I is equal to theta I by theta I, which is equal to h minus h by u. So which is also equal to h by u. Theta I is angle subtended by the image at I, which is equal to h dash by v, which is also equal to h by u. So theta I is equal to minus h by u. Why minus sign? Because image distance is, we are measuring the image distance opposite. So for u is equal to minus f, theta I is equal to h by f. So theta naught, angle formed by object, is h by d. Theta I, angle formed by image, is h by f. Write the equation for angular magnification, that is m is equal to theta I by theta naught. Theta I value is h by f. Theta naught value is h by d. When you simplify, you are going to get d by f. So the magnification caused by the simple microscope when the image formed is at infinity is d by f. When the image is formed at closest approach of distinct vision is 1 plus d by f. Compare these two equations. Here, in case of a relaxed view of eye, the magnification is, if d value is 25, if the simple microscope is of a focal length 5 centimeter, the magnification caused will be 5. For the same lens, the magnification caused when the image is formed at d will be 6. So 1 less than the magnification when the image is at near point. But viewing the image at a infinity gives a relaxed position of eye. So image formation at infinity is preferred more over the image formation at a least distance of distinct vision. Now this is about the simple microscope. Now using the simple microscope, you can have a limited magnification. At the most you can have a magnification of 9 or less than that for a realistic focal length. Realistic focal length means you can have a focal length of 5 or you can have a focal length of 4. You cannot have a focal length of 1 centimeter so that you can have a magnification of 25, because m is equal to d by f. If d value is 25, if you manufacture a convex lens of a focal length 1 centimeter, then you are going to get a magnification of 25, means your image is enlarged by 25 times that of the object. But in reality, in practice, it is not possible to manufacture a lens of 1 centimeter. So for a realistic focal length, you can have a maximum magnification less than 9. If you want to have an still enlarged image, then what to do? You have to use two lenses, a combination of two lenses to have more magnification. So for much larger magnification, we can use two lenses. So the microscope which is using two lenses is called as a compound microscope. So the schematic diagram of the compound microscope is shown here. So it is having two lenses. The one which is nearer to the object is called as objective, and the another lens which is nearer to the eye is called as eyepiece. So what is the job of these two lenses? The first lens is going to form the image of the object. Now this image is going to serve as the object for the second lens. This image formed by first lens is going to serve as the object for the second lens, and second lens just magnifies it. So the final image will be real and inverted. Now we'll see how the image formation takes place. Here, objective lens forms a real, inverted and magnified image of the object. So this is the objective lens which is going to place in front of the object. So it is going to produce an real image, inverted and magnified than that of the object. Now this image is going to be the object for second lens, which is nothing but eyepiece. So the eyepiece functions essentially like a simple microscope. What is the job of the simple microscope? Just magnifies the object or image which is in front of it, and then it produces the final image. The final image is enlarged and virtual. Now how to use this compound microscope? The lenses are adjusted such that the first inverted image should be formed at or within the focal plane. Why it should be at or within the focal plane of the second lens? Because if the image formed by the first lens is at a distance of focal length of a second lens, then the second lens is going to form the image at infinity, so that the eye can observe that image in a relaxed position. So we have to form the image by the first lens at a distance of focal length from the second lens. So from the ray diagram we can write the magnification for objective. So you all know it is nothing but a combination of lenses. So combination of lenses, the effective focal length 1 upon f is 1 upon f1 plus 1 upon f2. So the total power of the combination of lenses is the sum of powers of the two lenses. The total magnification caused by the combination of the lenses is equal to the product of the magnification produced by both the lenses, M1 into M2. So here in case of compound microscope, the total magnification caused by the system of two lenses, the total magnification caused by the system of two lenses is the product of magnification caused by first lens and magnification caused by second lens. That is nothing but M naught, magnification by objective, into magnification of the eyepiece. So to have this equation, total magnification, first we need to write the equation for M naught, magnification by first lens, and ME, magnification by the second lens. So first we'll write magnification caused by the first lens, that is M naught by the objective lens. M naught is equal to H dash by H. From the ray diagram you can see here we are considering two rays emerging from the object. One is parallel to the principal axis, another is passing through the optic center. So the one which is parallel to the principal axis, after refraction passes through the principal focus, and another ray which is passing through the optic center passes undeviated without changing its direction. So wherever these two rays meet is the image formation point. So from this diagram we can see magnification is H dash by H, which is equal to L by F naught. L by F naught. L is nothing but the distance between the focal length of two lenses. F naught is the focal length of objective, FE is the focal length of the eyepiece. The distance between these two is taken as L. So it is F naught divided by L. Let this be equation 1, where we are writing the equation for magnification caused by objective lens. As already we have told that the second lens eyepiece serves as a simple microscope. So we are using the results of a simple microscope to write the magnification due to eyepiece. So magnification due to eyepiece, ME is equal to D by FE. Usually it is D by F. As the focal length we have to indicate it is of eyepiece, we are writing it FE, subscript E. So the total magnification is M is equal to M naught into ME. M naught value is L by F naught into D by FE. So this is the total magnification caused by the compound microscope. To achieve this, a large magnification, from this equation you can tell we have to have the objective as well as the eyepiece should have the small focal length. Small focal length, then it is possible to have a maximum magnification.